Hey everybody, Mr. Johnston here, and we're going to take a look at the Quantifying Strength of Acids and Bases notes. We'll go through some of this together, and you have this packet in front of you, so follow along and add the notes to your packet. So the first point is we're going to talk about water. So water is neutral, meaning that it's right in the middle on the pH scale. Water is a really unique and special compound because it can act as both an acid or a base. It is what we refer to in chemistry as amphopoteric. So that just means that it can act as either acid or base. These equations here, these chemical equations, show us how water can auto-ionize. So think about this. If you have two water molecules, both as liquid, from time to time they're going to bump into each other with enough energy and enough of the right orientation to actually transfer one of these hydrogens over to the other molecule. The result of that is H3O, and that's a positive because now that hydrogen carries its charge with it. That is known as the hydronium ion, H3O+. And since this water lost a hydrogen, it's going to be just OH. That's the hydroxide ion. So this happens from time to time. This is auto-ionization of water. We can also think of this equation to simplify it a little bit. Anytime you see hydronium H3O+, you can think of that as a hydrogen ion. And of course, we've got hydroxide. Now, we know in reality that water doesn't just magically split apart like this, that really it's a collision between one water molecule and another that results in this transfer of hydrogen. But again, if we want to simplify things, we can think of it just like this equation. In chemistry, it's worth noting that anytime you see that hydronium ion, H3O+, to a chemist, that's the same as a hydrogen ion. So we think of those two as sort of interchangeable. We learned in our equilibrium unit all about equilibrium constant, K. And so we have an equilibrium constant for this auto-ionization process of water, and we call that the ion product constant for water. We write it just like any other equilibrium constant. We put a W in the subscript to indicate that this is the ion product constant specifically for water. Remember, when we write equilibrium constants, we do not include liquids or solids. So it's just these ions that are in the equilibrium expression. So it's the concentration of the hydronium ion times the concentration of the hydroxide ion. And again, whenever we see hydronium, we can think of it as a hydrogen ion. So we could also write Kw is equal to the hydrogen ion concentration, H+, times the hydroxide ion concentration. It turns out that Kw at 25 degrees Celsius is 1 times 10 to the minus 14th power. And so it's a constant. It's always that value, which means that if the hydroxide and the hydrogen ion concentration are equal to each other, that means those concentrations, those numbers, are going to be 1 times 10 to the minus 7th power molarity. And we're going to see on the pH equation in just a couple of minutes that if we have a hydrogen ion concentration of 1 times 10 to the minus 7th, that's going to result in a pH of 7, which we're going to see that is actually right in the middle of the pH scale. speaking of the pH scale, let's take a look at it. The pH scale runs from 0 to 14 with, as we said, 7 being right in the middle. That's the pH of pure water. And pH scale is a logarithmic scale. So I just want to do a quick review of how logarithms work. So logarithms are essentially counting by a power of 10 or a factor of 10. So if you have the number 1 and you take the log of that number, then that answer, log of 1, is equal to 0. If you have the number 10 and you take the logarithm of that, you have an answer of 1. If you take the log of 100, so I'm going up by factors of 10, the log of that is 2. Log of 1,000, that's 3. So when we change from like 4 to 5 on the pH scale, that's a change by a factor of 10. And it actually works the other way as well. If you have 1/10, well, that's going to be, the log of 1/10 is going to be -1. On our pH scale, we don't have negative numbers, and so what we end up doing is we take the negative log, and it ends up making that number positive. So the negative log of 0.1 would be positive 1. If you had 0.01, and you take the log of that, that's going to be -2. If you take the negative log, that's going to be +2. And so, again, the reason I'm showing you this is the pH scale is a logarithmic scale. We're counting by factor of 10. And it is worth noting here that there is an inverse relationship between hydrogen ion concentration and hydroxide ion concentration. If you think back just a second ago, we had this Kw expression. So this number, Kw, is always the same. It's constant. That means if we increase the hydrogen ion concentration, if this number goes up, well, that means the hydroxide ion concentration has to go down. So the more hydrogen ion is in the solution, the less hydroxide ion is in solution, and vice versa. The more hydroxide is in solution, the less hydrogen that's in solution. We do have a couple of equations that you need to get down, and you should probably just put these equations to memory. So the pH equation is negative log of the hydrogen ion concentration. And also keep in mind that we can interchange this with hydronium ion concentration. So a lot of times you might see the pH equation written out like pH is equal to negative log of hydronium ion concentration. And again, that means the same thing whether we have hydronium ion or hydrogen ion. Those are interchangeable. We can also do, it's less common, but you do see it sometimes, POH. That is negative log of the hydroxide ion concentration. And from these equations, we can actually rearrange the equation a little bit and solve for the concentration variable. And when we do that, the new equation looks like, if we solve for the hydrogen ion concentration variable, it's 10 raised to the power of the negative pH. And if we do solve for the hydroxide ion concentration, then we're going to get 10 raised to the negative power of the POH. Another relationship that's worth noting right here is that pH plus POH is always equal to 14. That's sort of the magic number is 14. And it actually comes back to that KW. Since KW is always 1 times 10 to the minus 14th at 25 degrees Celsius, pH is always equal to, pH plus POH is always equal to 14. And then we already wrote down this equation, but it's worth rewriting. KW is hydrogen ion concentration times hydroxide ion concentration. And that number again is 1 times 10 to the minus 14th. So now that we have some equations, we can actually use those equations to find like hydrogen ion concentration and pH of strong acids. The first thing to note about strong acids is that they completely ionize. Strong acids completely ionize. And so this is not an equilibrium, it's a one-way arrow. So if you have a strong acid like HCl, it's going to completely ionize. That means it's going to transfer its hydrogen over to water to form chloride ions and hydronium ions. And both of these, by the way, are aqueous. And so what that means is if you have a solution of HCl that is 0.15 molar, well, that 0.15 molar results in a solution that's 0.15 molar of chloride and 0.15 molar of hydronium. And so with that, and remember we said that hydronium is the same as hydrogen ions. So if we know the hydronium ion concentration is 0.15, then the hydrogen ion concentration is 0.15. And with that, we can find the pH because pH is negative log of the hydrogen ion concentration. So I know the hydrogen ion concentration, so I just got to plug it in on my calculator. So negative log of 0.15. That means the pH is 0. And I can round this to 824. pH does not have a unit, it's just the number. We can do something similar with strong bases. So strong acids are pretty easy. We just take that concentration, plug it in, and we've got the pH. Strong bases, this is going to completely dissociate, so you end up with sodium ions in solution and hydroxide ions in solution. So again, when we talk about strong in terms of acids or bases, we just mean that it completely ionizes, or in the case of base, completely dissociates. So if we know the concentration of the sodium hydroxide, then ultimately we know the concentration of the sodium, which we don't really care about, but we do know the concentration of hydroxide is 0.215 molar. So the hydroxide ion concentration is 0.215 molar. We want to find the pH. So I would say the easiest way to get there is using this relationship. if we know POH and pH, we know that the sum of those two is 14. And so if I find the POH, I can use that to find pH. So let's do that. POH is going to equal negative log of the hydroxide ion concentration. So negative log of, so I got a POH of now, again, we want to find pH. It's going to be 14 minus POH. So I just rearrange that equation a little bit. In this case, we know the pH, if I take 14, is going to be 13.33. And again, on the pH scale, just going back a little bit to this, this would be, the closer you are to 14 would be more basic. The closer you are to 0 is more acidic. So on this one, on our example, this is really, from the first calculation, this is really quite acidic because we're getting close to that 0 number. And this one is really quite basic because we're getting close to that 14 number. And we'll go through weak acids and weak bases a little bit later on in class.